just like we have linear momentum, there is also angular momentum, and we can do the similar extension to the angular case as we did for momentum as we did for energy. Remember, momentum in the linear sense is P is mv. The more mass and the faster something is going, the more momentum it has. It basically describes how hard it is to stop something. Now, the same thing is true in the angular sense. We usually give angular momentum the symbol L, and it is equal to not mass, but moment of inertia, and not velocity, but angular velocity. So L equals I omega. Now, what's really cool about this is the same law still applies. Angular momentum is conserved. And this actually sort of explains what's going on when you were little, or maybe you still do it, when you took your swing and you twisted up the chains, and then you sat here and you were like, wee, and you kicked your legs out and you slowed down. And then you brought your legs in and you sped up. Why would that happen? Well, your momentum's not changing, or your angular momentum's not changing. If you kick your legs out, you've distributed more mass farther away from you, which means you've increased your moment of inertia. And as a result, your angular velocity has to decrease. Whereas when you pulled your legs in close, you brought your moment of inertia down, so your angular velocity would increase in order to keep your angular momentum the same. So just remember, basically when we're going from linear things to rotational things, mass gets replaced by moment of inertia, velocity gets replaced by angular velocity. And do be sure that you're measuring angular velocity, angular acceleration in radians per second.